All please observe. So now, when the south pole is pushed away from the magnet, away from the solenoid, then you can see the deflection will take place towards the right side and the current will pass anti-clockwise direction, similar to the case 2. Now, let me come to the case 1 again from the first case. So first case, what is happening, guys? All of you check it. Bar magnet is kept stationary away from the solenoid, so that what is happening? No deflection in the galvanometer, means pointer is indicating 0. First case, how many of you understand? When you kept the bar magnet away from the solenoid, then no current is induced in the solenoid, so that it is indicating 0. Are you clear with the first case, everybody? Yes, Kevin? Now, the second case, what? I am pushing inside which pole? I am pushing the north pole of the solenoid, north pole of the bar magnet into the solenoid, so that what is happening? So the galvanometer is deflecting anti-clockwise, means right side, so that the current is moving in the anti-clockwise direction. Okay. So by that time, if north pole is going inside, then solenoid is also that side north pole will be there and opposite will be the south pole. So the current is moving anti-clockwise direction. Deflection is towards to the right side galvanometer. This is the second case. Now, third case. Again, the bar magnet is kept stationary inside the solenoid. Inside the solenoid, then you can see no current is produced. So again, the galvanometer pointer is indicating no deflection. So 0. Galvanometer pointer is indicating at the 0. Now, the magnet which we kept inside is pushed outside. Okay, means north pole is coming outside. So by that time, the galvanometer, again the current is induced. By the time the current is moving clockwise direction means galvanometer deflecting towards to the left side, and by the time here south pole and here north pole of the solenoid will be existed. Is it okay, Kevin? Arvind? That is what you have to remember. Here north pole and here south pole will come. Now, if you notice it, next, fifth case, instead of now north pole at the point B is completed. Now what we are going to study? Now south pole. So south pole is going inside. Remember, going inside, then that is the south pole. Then if you'll see in this case, the current is moving, understanding, clockwise direction. So the deflection will take place. Same to it is a deflection towards the left side and the current is moving in the clockwise direction. So here south pole, here also south pole. So on opposite north pole will be there. Now sixth case what it is? I kept inside stationary. Again, what is that? No deflection, or pointer is indicated at the 0 point only. Now, when I pushed outside, all of you remember, when I pushed outside, then you can see here the south pole is pushed outside. Then here the solenoid will be north pole. Here it will be the south pole. Then you can see, like a similar case to second case, the current is moving in an anti-clockwise direction and deflection is towards the right side. Is it okay, everybody? So this is what the 7 cases in the solenoid. When I placed at the point B, if I push in or push out south pole and north pole, and as well as kept stationary, these are the deflections will take place. And this left, right, and clockwise, anti-clockwise is only very, very important for our exam. So anything anybody is having doubt in these 7 cases, kindly ask me. I will explain once again. Please, anybody, Nitish, Ashika, Kavya, please respond. So this is what the things which is second activity demonstrating the phenomena of electromagnetic induction by moving a magnet near a solenoid. So if I'll move, how it will be current is passing and what is the deflections, you have to remember very carefully. Now you remember the same activity. Now here, who is constant and who is moving? Anybody can tell me? Here solenoid is constant and bar magnet is moving. Yes or no, guys? Please respond. Here a solenoid we kept.
Sure.
Wait. A solenoid I kept constant and bar magnet is moving to and fro motion. Or else If we'll demonstrate the same experiment that magnet is fixed, understanding, magnet is fixed, anything, and if a solenoid is moving, understanding, moving the coil towards or away, towards and away from the magnet, then also it will be shows the same deflection. So both the experiment is same, away from the magnet. It is also observed that the galvanometer shows the deflection. Okay, guys. It is observed that galvanometer shows deflection as long as the coil is moving. So whenever it is moving, remember all of you, only during observed motion only it will produce the current. When it is stopped, then no current is produced. That is what you have to remember. Either bar magnet is moving or else the coil is moving, then only the current is produced. This is what about this experiment. Now somebody is asking something, you can ask me, I will explain. Anyone? Yes, please. Respond me. Yeah, please tell me.
Sir, show case 5 and 6. Sir.
Case 5 and 6. Yeah. Case 5. Case 5 is south pole is going. South pole is going inside. Remember, it is pushed in. Completed, guys?
Yes, sir.
Everybody? Now, this is what about all of you remember this. So now, if you'll notice it here, so these are the factors. Let us see what is the factors which will increase. Like we can make some conclusions make from this. That is what very important for us. So now if you'll notice it here, the induced current is produced in the coil only when, Karthikeyan, only along as there is a relative motion between the coil and the bar magnet. Means a bar magnet is going inside and coming outside, going inside and coming outside. Then only we are observing momentary deflection. That is what you have to use a word called as momentary deflection in the galvanometer. When only during the relative motion, moving, going inside and coming outside. That is the first thing. Next, the direction of the deflection of the galvanometer is reversed if the direction of motion of the bar magnet is reversed. Means if the bar magnet going inside, galvanometer deflecting into one side. If it is coming outside, the galvanometer deflecting into the another side. That is what you have to remember. And also you see the polarity of the bar magnet is in motion is reversed. Then also the deflection is reversed. Yes or no? North pole is going inside, some side deflection. South pole is going inside, another side deflection. Yes or no, Arvind? Everything? So these are the factors which we have been observed, the conclusions which can be drawn from this. That is the three points you have to remember. And the third point is the strength of the induced current depends on three factors. What is the three factors? Anybody can tell me, guys? What is the strength of the induced current is depend on three factors. What is the first factor? Anyone? Anyone of you? How the strength of the induced current depends on? First of all, strength of the magnetic field means a bar magnet what I am taking. If it is more stronger, more current is induced. If it is less stronger, less current is induced. The strength of the magnetic field. That is only bar magnet. Okay, this is the first factor which will increases or decreases the induced current. Strength of the magnetic field means the strength of the induced current increases with the strength of the magnetic field, or we can say power of the magnet. More powerful magnet, more current is induced. Less current is less powerful magnet, less current is induced. So as we know, induced current is directly proportional to magnetic field. B means power of the magnet. That is the first factor. Second factor, number of turns. This is not a common, this is not new thing. Already we know that number of turns in the coil. Number of turns in the coil. So now you tell me directly or inversely proportional, both, Bhumika? Number of turns. Number of turns, understanding, is directly proportional to the induced current. So more number of turns, more current is produced. If less number of turns, less current is produced. So induced current you can take. Induced current is directly proportional to the larger the number of turns in the coil, stronger in the induced current. That is what you have to remember. Now, third factor. So these two factors everybody knows, but third factor is also very important. That is what? Speed. So how you are moving the magnet inside the solenoid, slowly or fastly. If you are moving fastly, going inside, coming outside, going inside, coming outside, going inside, coming outside, like that, moving very, very fast, then more current will be induced. Higher the relative speed, that is what we used to call it as relative speed. Understand? So relative speed we used to call it as, so relative speed between the coil and the magnet. Coil and the magnet. So we can say relative speed is V. So relative speed is directly proportional to induced current. So relative speed means the motion of the magnet and as well as or else the coil between them. That is what. Higher the relative speed, then the stronger is the induced current. So these are the three factors which will influences the induced current. Any doubt, anybody, you can ask me. So this is what you have to remember, all of you. Karthikeyan, hope you all understand this. So these are the three factors how we can increase the induced current and the conclusions made. So from this experiment, we have to make some conclusions. So what is that conclusions? All of you tell me. First of all, what is the first conclusion, Arvind? So as we know, three factors which will influence the induced current. Okay, now what is the conclusions we have been made? Only the induced current is producing where? When a law, understand, as long as there is a relative motion between the coil and the bar magnet. That is the first thing. Okay. So please all of you write. The induced current is produced. The induced current is produced in the coil as long as there is a relative motion. Relative motion between whom, Nitish? Relative motion between the coil and the bar magnet. That is the thing. Next, second conclusion. If it is kept stationary, either inside or outside, then no deflection. That is. Next, the direction of deflection. The direction of deflection. Is it reversed or not, guys? Every time it is reversed. Going inside one direction, coming outside another direction. The direction of deflection in the galvanometer. Is reversed if the direction of the bar magnet is reversed. If the direction of the bar magnet is reversed, or the polarity of the bar magnet in motion is reversed. The polarity, either south pole or north pole. The polarity of the bar magnet is magnet in motion is reversed. So these are the conclusions which we have been made from this activity. So in this, anybody is having doubt, you can tell me. So now you can see when it is going inside and coming outside, it is showing a different directions of the current. So that is why these current only we used to call as alternative current. What we used to call, guys? This is only we used to call as alternative currents, we used to say that. Okay, so these are the three factors. By increasing the number of,
Can you please show the conclusion, second point?
yeah, I will show you. So this is the second point. You can see, yeah, this is the second point. So now if you see, by increasing the strength of the magnet, we can increase the induced current, or by increasing the number of turns, or by increasing the speed of rotation of the coil or the magnet, means going inside and coming outside, then we can make it. So that is what we can say, movement or motion or rotation going inside and coming outside, then we used to get the induced current more, it will be induced. So this is all about demonstrate electromagnetic induction by using a coil and a bar magnet. So hope you all understand. So anybody is having any doubt here, you can see. Now you can see here we can find this direction of magnetic field and induced current and everything by using two rules actually. But class 10th you will study only single rule, and 12th class you will study another remaining rule. So we can use it here like electric motor, how you use Fleming's left hand thumb rule. Here we can find the direction of induced current. Understand everyone? So direction of induced current by using the two methods. So one law is called as Lenz's law, which we will study in the 12th class. It's not now needed. Now the second law only we will study in the class 10th. That is what you all people knows already. What is that? Fleming's right hand thumb rule. Okay. So now right hand thumb rule is we are going to use it to find the direction of induced current. So now that one I will teach you. So now if you'll notice it, the direction of induced current. So if you'll see all the textbook they have been given. So if you'll see, if you'll place your right hand, three fingers like left hand. So again the same thing. The thumb is indicating. Understand? So the thumb is indicating what, guys? The motion or movement, and our the middle finger is indicating what? The middle finger is indicating always what is indicating, Ra? The induced current, and our forefinger, that index finger is indicating the direction of magnetic field. So now that I will show you that you can write it also clearly. So that induced current, and as well as here we will use, see, there we will use what? Fleming's left hand thumb rule, we used to find the direction of force. But here we will use the Fleming's right hand thumb rule to find the direction of induced current. All of you that you have to remember, induced current. So this is what you can take the diagram. So we are having, if you take your right hand, we'll be having a three fingers. So this is the index finger, if you'll notice. So index finger is indicating magnetic field, which is pointing towards the west, you can see. So west direction, magnetic field, and motion, if you'll notice it, vertically downwards, this is what? Thumb, and induced current is north pole. It is indicating north because all should be 90 degrees each other. So this is what? North pole it is indicating. But here if you see, it should not draw north pole means straight line, because all they should be perpendicular to each other. It is a Z axis. That is why we are drawing like that. Okay. So that is right hand thumb rule, Fleming's right hand thumb rule. This is the rule which we'll use to find out the direction of induced current. Remember all of you, direction of induced current in a conductor which is moving perpendicularly to the magnetic field. Always the induced current, understand, induced current is perpendicularly symbol is this one. This is a perpendicular symbol. So perpendicularly to the magnetic field. All of you should remember. So to find this only, we will use this Fleming's right hand thumb rule. So Fleming's left hand thumb rule, we will use to find the force, means the thumb, the motion which is exerting. So here we should not say force, we should say as a, what we should call, guys? Thumb is indicating movement of the conductor, or we can say motion, we can say, or else you can write movement of the conductor. So, but left hand thumb rule, what we used to call that one as, the thumb is called as force exerting. You can see left hand thumb rule, the thumb is called as motion only, but there we used to say force, the movement of the conductor. So here also the same thing, movement of the conductor, or we can say motion, that is the thumb. So all the same thing, left hand and right hand same, but left hand there we used to find the movement of the conductor, but here it is, we are using for right hand for finding the induced current. So now this rule we can use the activity which we have been done for this one, or last class if you have noticed it. So we have been done the last class, the current carrying straight conductor is moving between the two poles, that is what horseshoe magnet. So in this case, how the diagram, how we can apply Fleming's right hand thumb rule, now we will check it. So now if you notice it, all of you, you take your right hand and you tell me. So let me see who will say. Now if you check it very carefully, this is what the experiment which we have been made. So this is the current carrying conductor which has been kept like this. So this is, I am making galvanometer. So now this is what it is. So I have been placed, this is the north pole and this is the south pole, horseshoe magnet. So now here like this it is moving, or else your choice, whatever it is. Now you tell me, here you apply the Fleming's right hand thumb rule and you tell me what is the direction of induced current and everything. Let me see who will say. Anyone? Fleming's right hand thumb rule. Apply it and tell me. Yeah, please respond. How it is? Suppose, imagine. Now, what is the direction of magnetic field? All of you keep it. So now, direction of magnetic field always from where to where? We already know that. From where to where, Kevin? Direction of magnetic field.
North to south.
South. Yes or no? That is what you have to imagine. Now, north to south, the magnetic field is always active. Now imagine, as we know that now the conductor is moving upwards. Let me imagine the motion is upwards, motion or movement. Conductor is pushed up. Either we can pull down or push it up. Yes or no? Yes, please respond. Now imagine the conductor is pushed up. Now you tell me how the current is induced. From B to A or A to B? Let me see who will say first. Let me imagine this is the B point of a conductor and this is the A point of a conductor. Now it is coming up. I am taking up and pushing down. As we know, both the cases it will be deflecting into opposite direction. Now apply your Fleming's right hand thumb rule and you tell me how it is happening. You can easily, we can find it. Magnetic field and thumb is upwards. Fleming's right hand thumb rule, exactly like the picture given in the textbook. So now you tell me current is induced from where to where? From B to A or A to B, just you apply. See, you can, your thumb is B point, your thumb is indicating upward and magnetic field is indicating towards the north pole to south pole. Now your remaining middle finger will come which side? Check it, all of you. Which side it is coming? It is coming downward direction. It is what? Induced current. You can check it. So in this case, the current is moving from B to A. This is what will happen. You check, all of you check it, all of you. Sorry, I'm making wrong here. So it is making from A to B. This is what. So now, is it correct or not? Everybody verify. Yes, please respond. As I told you, in front of the page, you have to imagine. And you can make it, definitely you will get the answer. Everybody verify. Now if you will reverse, if you will push out, if you will pull down, then you can see, then the current will be induced from A to B. Now I will show you. Now you can notice my hand, if you will observe, then you can able to understand. So now all of you see me. Can you able to see me now? Respond. Yes. Now, for example, see, this is what Fleming's right hand thumb rule. Yes or no, guys? So textbook also giving like this. Correct, Amma? So for me, I'm keeping like this. So 90 degrees all. So between this and this 90 degrees and between this and this 90 degrees. Now in this thumb is indicating what, guys? Respond me. What is this thumb is indicating? Motion. Yes. Please respond. Motion. And this is indicating magnetic field. And this is indicating the induced current. These are the three we have been studied. So now what they are saying, so this is imagine horseshoe magnet. Now the conductor is moving like this, up and down, up and down, up and down. Now I am applying. Now conductor is pushed up like this. Up means what? Motion is upwards. Means my thumb is upwards. Now, as we know, this is horseshoe magnet, north pole, south pole. This is north pole, this is south pole. So that like this it is there. So now north pole to south pole, the magnetic field is acting like this. Yes or no, guys? Like this, the north pole is acting magnetic field, north pole to south pole. So magnetic field direction is like this, and this is the force or motion of the conductor. Now you can see my remaining finger, if you make both 90 degrees, then how it is coming? The current is coming from downward direction, means from B to A it is coming. So if you take it here, the conductor from B to A current is passing. Now for example, if it is pushed down, you can see push down means my thumb is going downward, but still the magnetic field is acting like this. So now you can see by the time the current is acting from A to B, because it will be reversed, because like that by the time it will come. So still the motion of the conductor is downwards, and the magnetic field is acting like this, north pole to south pole, so that by the time the conductor is, what is that? The current is moving from A to B. Like this it will go. Reversed. We can reverse the direction. So that is what we can find the induced current. If we'll see, for example, if I'll reverse the motion, now it is upwards. Now if we'll take another, this is the south pole and this is the north pole. Now the conductor is, you can see the galvanometer I have been connected. Now the conductor is downward direction, means the thumb is downwards, and still the magnetic field is acting like this only. So by that time, the induced current moves from A to B, so that it will go from A to B, it will be. So like this it will be, keep on reversing. Now here you can see from like this it is going. B to A it is coming. Now it is going from A to B. That is what it will be reversed. You can see. First case, you imagine this is the direction of magnetic field and this is the movement upwards, so that my thumb remaining finger is indicating, middle finger is downward direction. So from B to A. Now reversed case. Now the conductor is going downwards, magnetic field is still acting like this. Now my remaining middle finger is indicating upward, so that current it is moving from A to B. Like this it is indicating. So this is the things which you have to remember. So it is two-dimensional current. So that is what you people might be not understanding. So now downwards means the thumb indicating like this. Imagine guys, thumb indicating like this. Understand? So exactly see, my downwards means I will keep like this. Now you can see my remaining finger is indicating upwards, correct guys? So like this it will come. All of you imagine like this it will come the picture. So now you can see from B to A and A to B, not upwards. Don't imagine. This is a two-dimensional I am drawing. So if you imagine this is the conductor, all of you see. Now magnetic field is acting like this. And it is pushed down. Pushed down means remaining finger is indicating like this only. Yes or no guys? Check it all of you. Remaining finger is indicating from where A to B it is going. So that is what is pushed down. Now push it up. Push it up means what? My thumb will come up like this. My thumb will come off. My still magnetic field is acting like this. This finger you can see, this finger is coming like this direction, so that it is B to A. Are you clear everybody? So this is what we can use the Fleming's right hand thumb rule to find the direction of induced current. The same one if you'll apply for the solenoid also, we can find the direction of induced current by using a Fleming's right hand thumb rule. So this is what the second activity which we will study, the electromagnetic induction. Now we have a third one, that is what by help of current we will produce the induced the current, that we will study in the next class, or else offline class I will finish you. So that is the third experiment. Means till now we have been studied inducing the current with the help of magnet. Now we are going to induce the current with the help of electricity. Means with the help of electricity only we are going to induce the electricity, induced current. So that is the third experiment. So that will demonstrate either in the class, offline class, or else next online class will finish it. So this is all about it. So till here anybody is having any doubt, you can ask me, or else you can leave from the meeting. Hope you all understand this. Any doubt, anybody can ask me. So that is experimental. Very important. That is also I will say. So with this I will leave you. Thank you so much, and all of you come by afternoon. Thank you all.
Sir,
Yeah, please ask me. Ask me. Somebody is
sir,
asking.
can you please teach the second case, sir?
Which is second case? Moving up. This is Kavya.
Yes, sir.
This is this.
Yes, sir.
Now you can see. Observe my hand. Now you can see this is what the conductor. So as we know that conductor is this is A point and this is B point. Now conductor is pushed down, one time up, one time down. So when I'm doing the oscillation like this, then only I can see the deflections in the galvanometer. So going up also current will be induced, coming down also current is induced. Relative motion. Now it is down in the sense of C. My thumb is indicating motion of the conductor, motion downwards. Now magnetic field is still what? North pole to south pole, like this only. So like this, the two fingers are like this. Now remaining finger is C, towards to you it is pointing. So current is passing from A to B, like this. Understand, Kavya? Now if I'll reverse it, pushing up, understanding, pulling up, you can see by the time my thumb will be coming like this. My thumb is going upwards and still the magnetic field is like this only, you can see. So by the time this finger, middle finger, you can see it is pointing towards to me. So that current is coming from B to A. Understand, Kavya? Clockwise. Okay.
Yes,
So if it is moving up, current is coming clockwise direction. Okay. Now galvanometers, it will be clockwise direction. Means it is rotating right side. So galvanometer deflecting like this. Sorry, anti-clockwise direction. Galvanometer deflecting right side. It will come like this, B to A. Now if it is pushed down, then it will go from A to B. Like this it will. Okay, Kavya.
yes, sir.
That's fine. Thank you, everybody.